Hello everyone. In this video, we will be discussing about failure modes of engineering materials. Mostly we will be discussing about the ductile fracture and the brittle fracture. So first we'll start the session with the definition of the failure. So since I'm talking about the engineering materials, let me define the failure as a fracture. So how can we define fracture? So simple fracture is nothing but separation of the body into two or more pieces in response to an imposed stress that is static. So static means we know that a constant load or a load will be applied gradually with respect to the time. And a fracture is the separation of a object or material into two or more pieces under the action of stress. And the fracture of a solid usually occurs due to the development of certain displacement discontinuity surfaces within the solid. If a displacement develops perpendicular to the surface of the displacement, it is called a normal tensile crack or simply a crack. Or if a displacement develops tangentially to the surface of the displacement, then it is called a shear crack or slip band or dislocation. So I'll be explaining all these concepts in detail in the coming slides. The fracture strength or the breaking strength is the stress when a specimen fails or fractures. So as I told you, we have two type of fractures which we'll be discussing in this video, that is the ductile fracture and the brittle fracture. First is the fracture mechanism. We'll have a detailed look. The fracture mechanics is the field of mechanics concerned with the study of the propagation of cracks in the material. In modern material science, fracture mechanics is an important tool in improving the mechanical performance of mechanical component. It also applies the physics of stress and strain, in particular the theories of elasticity and plasticity, to the microscopic crystallographic defects found in real materials in order to predict the macroscopic mechanical failure of bodies. Here I can able to see the different modes of the fracture. So the mode 1 is nothing but the opening of the component, and mode 2 is nothing but in plane shear. You can able to see that the on the surface the loads are acting in the opposite direction, and third one is nothing but a like a out of plane shear. You can able to see that here it is acting in this direction. And coming to the brittle and the ductile fracture, how it happens, this is the real models. So here we can able to find out which is the brittle and which is the ductile one. So assume that if this is the shape of the original specimen, so if it is a brittle material means the fracture will happen like this. You can able to see this. It there will be an unequal metal. Um, there will be an unequal metal flip where you can able to see this, and the crack can happen at any place. But moving to the ductile fracture, where it tries to, when the stress is imposed on it, it tries to elongate to the maximum core. So once it loses or once it crosses the yield point, then only it leads to failure. So in case of the brittle, without any the pre-sign, the failure will happen. But in case of the ductile, so it tries to elongate, even it tries to change its shape, and finally once it could not able to sustain the yield point, and once it is crossing it means then only the failure will takes place. These are all the examples of both. This is for the brittle and this is for the ductile. So the ductile in detail we'll discuss here. When a ductile material has a gradually increasing tensile stress, it behaves elastically up to a limiting stress, and then plastic deformation occurs. So as stress is increased, the cross-sectional area of the material is reduced and a neck region is produced. So with a ductile material, there is a considerable amount of plastic deformation before failure occurs in the material, and even there is a considerable amount of failure occurs in the neck region. So you can able to see this. So initially it was a straight body. When the tensile load is applied, so the when the load is trying to distribute, so when it is when the static load is magnitude is keep on increasing, the neck region will be produced. And when the load point, when the load is continuous means, even there will be a gap will be producing in the neck region, and finally this gap region leads to A big like a big gap will be produced, and finally it leads to the removal of material from the component. And steps in the ductile fracture, we can name it into four steps. First one is the necking. Second one is this creating small cavities. And third one is nothing but formation of the crack. And last one is the cup and cone fracture. And here the necking is very clearly explained. So a tensile force is applied. So what is necking? So in engineering or in material science, we can call it as a mode of tensile deformation where a relatively large amount of strain localized disproportionately in a small region of a material. So with elastic strain, the material becomes plastically deformed and a neck formation process starts. And even the deformation of the material depends upon the material purity. And the small cavities forming within the neck, small cavities you can able to see, even we can also call this a voids, so which are formed. So these develop as a result of the stress causing small particle of impurities or other discontinuities in the material to either fracture or separate from the metal matrix. More such nuclei are available to trigger the development of these cavities. The less the material will extend before fracture and the less the ductile material. So as purity of material increases, ductility of the material also increases. So if you are going with a material where which is having more voids or more cavities, means that is due to the impurities present in the material, the chances of cavity forming will be more. So if you want to avoid any kind of fracture, means always try to use a material which is at its purity. Then how the crack is formed. So the small cavities, or even we can call it as a micro voids, which form in the interior of the cross section, which enlarges, come together and which coalesce to form an elliptical crack which has its long axis perpendicular to the stress direction. You can able to see this. If this is the direction of the load applied, means always the crack will be formed perpendicular to the load applied direction. So the crack continues to grow in a direction parallel to the major axis by this microvoid coalescence process. If until or unless if we stop the load application, the crack will keep on increasing. Then moving to the cup and cone fracture. So finally the fracture ensures by the rapid propagation of a crack around the outer perimeter of the neck by shear deformation at an angle of about 45 degree. With the tensile axis, this is the angle at which the shear stress is maximum. Sometimes a fracture having this characteristic surface contour is termed a cup and cone fracture because one of the mating surface is in the form of a cup and other like a cone. So in this type of fractured specimen, the central interior region of the surface has an irregular and a fibrous appearance, which is indicative of plastic deformation. Then moving to the brittle fracture, the second type. As I told you, the brittle fracture takes place without any appreciable deformation and by the rapid crack propagation. The direction of the crack motion is very nearly perpendicular to the direction of the applied tensile stress and yields a relatively flat fracture surface. When gradual tensile load is applied on material in tensile stress at the end of elastic limit without any prior indication, material breaks. So this type of fracture is called as the brittle fracture. Examples we can say glasses, ceramics, and some types of the composites. So the factors which really affect the fracture are stress concentration, where the notch sensitivity, this topic will be discussing in detail. Then the speed with which the load is applied, the temperature, and the thermal shock loading. So with this the video gets completed. Thank you.